Phillips. I'm the training manager here at Lochinvar, and I want to thank you for taking the time out of your schedule this morning to join us as we talk about the various parts and pieces of the PowerFin product. Now, before we get started, I have a couple things I want to go over with you. First, if you have questions, there are a couple options to get those questions to me. The first would be to use the Q&A feature on your screen. You can manually type those questions in, and that will notify me, and I will be able to answer those questions for you live as we're going. That's one option. The other option is if you would prefer to actually ask your question or talk about it, use the raise your hand feature, and that'll allow me to know that you have an actual question that you actually want to speak, and I can give you the ability to unmute yourself. Unfortunately, as a webinar, they don't give you that ability right off the bat, so I have to give you that. So if you want to talk about it, just raise your hand. I'll be able to unmute you, and we can go from there. All right. Secondly, we are recording this webinar. So once we get done with this, probably by Monday, we will have this up on our website at lochinvaru.com, our training site at lochinvaru.com. So you can, if you have someone who's missed it, that'd like to go back and watch it, or if you just want to use it as a refresher, you can go back and watch it probably, like I said, after Monday. There's also, if you want to look at, there's a huge selection of other videos that we've already done, other webinars that we've recorded on that website as well, so you can go back and catch some of the other ones too. All right, and again, that's on our training site, lochinvaru.com. All right, so let's jump into this thing. So we're here to talk about, there we go. There we go. So we're here to talk about the various parts and pieces of the PowerFin models from 500,000 to 5 million BTUs. So this is what we're going to be looking at is pretty much the current production models today. And before we do that, though, I do want to talk a little bit about history. And I think it's kind of important with this particular product to give you a background on it. Some of you may be already familiar with this, and if you are, just please have patience with me. But I think it's important because I would say that without this product, Lochinvar probably wouldn't be where we are at today. This product pretty much put us on the path to where we are. So it's a very important product to Lochinvar. Even though it's no longer our current flagship, the Crest is our current flagship today, so it's no longer that. It's still an important product for us even today. But this model, as you see here, was introduced in 1986. The group of people that you see there in that picture, believe it or not, is everyone that worked, or pretty much everyone that worked at the manufacturing facility in Nashville in 1986. So that is a very, very small group of people. Now, when I joined the company 5 years later in '91, it had already expanded due to the growth. The growth was due to the PowerFin product. So it actually expanded quite a bit when I joined the company. But in '86, this product was introduced, 4 sizes from 250,000 BTUs to 1 million BTUs. Single stage on-off type operation, no modulation. But it introduced a lot of features at this point that weren't seen, wasn't available on products. So you had a very small footprint, very high non-condensing thermal efficiencies of 88%. Fan-assisted combustion, the diagnostic control panel. So you didn't see this on a lot of products at this time. So it's kind of revolutionary. Now, this product, as you see sitting there, didn't change a whole lot throughout its life. There were a few cosmetic changes to the outside, but pretty much that was about it until about 2005, realistically. The combustion system, the control system hadn't really changed from 1986 to 2005. Now, in 2001, we did introduce 3 larger models, 1.5, 1.7, and a 2 million. But while it shared the same name and shared the same vertical style chassis, completely different control system, completely different combustion system, so they were really different products. In 2005, though, they kind of brought the whole family together, and the smaller models went through its first major revision. So we still kept the vertical chassis, but we did away with the combustion system. At this point, we went to a negative regulation combustion system, redesigned the heat exchanger a little bit, went from a gasketed heat exchanger to a gasketless heat exchanger. A little bit different on the control system. Also gave modulation. So instead of being an on-off type product, allowed it to have a 4-to-1 turn down. So a lot of changes took place in 2005. We also did away with the smaller model. The 250 went away, and then we added a 1.3 to kind of fill that gap between the smaller products and the larger products at that point. 2007, we introduced the Smart System Control platform to it. And then 2017, we added the larger models, the current larger models, the 2.5 to 5 million BTU models, as well as introduced the Smart Touch platform to all models across the board. So that's kind of where we are at today. And those, like I said, will be the products that we're going to discuss. All right. But again, just want to give you a little background about this product. And like I said, it's a very important product to Lochinvar in regards to its history. All right, so let's talk about the system and let's talk about heat exchangers. The heat exchanger is the heart of the unit. It's the heart of any unit realistically, right? This is where your fluid is flowing through. This is where your heat transfer is taking place. So basically, without a good heat exchanger, your unit is going to suffer, right? So you have to have a good solid heat exchanger to start with. In this case, we have, again, had that vertical chassis. You've got a bunch of copper tubes in this heat exchanger, and because of the number of tubes that we have, and because of the design of it being a 360-degree round heat exchanger that completely surrounds the burner, you have multiple passes. In this case, you have 4 passes. Your typical horizontal copper heat exchanger, like what you might see on a copper fin or a copper fin 2, is typically a 2-pass design. Here we get 2 extra passes because of the number of tubes, and because of that we get a little bit more contact time between the water and the flue gases, which helps improve our efficiency a little bit. The headers, we still go with cast iron headers, but here we've gone gasketless. With the original models, you had a gasketed top and bottom header. And as you know, if you've got a gasket in a heat exchanger, that is your weakest link. If there's going to be a leak, it would be at a gasket. So we've completely removed that. So we have a solid cord 1-piece headers, top and bottom. All of the machine work will be done here at the facility. So we will get the raw materials in. So those raw headers come into us from the foundry. We will do the drilling, the tapping, the lining here if it needs to be done. The copper comes into us as a raw copper, thin copper tube. We will cut and defin those tubes the length here. So if you've ever been to the factory and done the factory tour, you've seen this process. So all this will be done here at the factory, as well as the assembly of the heat exchanger is done here as well. So once we get the raw materials in, we get it prepared. They go over to the assembly line, where we have an assembler who will basically start with the bottom header, put the appropriate number of tubes into position, put on the top header, and then basically roll or press each one of those copper tubes into the header using the rolling tool. Again, no gaskets. You eliminate the gaskets, we eliminate the leaks at that point. So this is a long process because you can have anywhere from 20 to 60 tubes depending upon the heat exchanger. So it does take a while to actually build this heat exchanger. Once all the tubes are rolled into position, then at that point we will do a hydrostatic water pressure test of 1.5 times. Again, all these heat exchangers are approved for 160 pounds of pressure. So that means they're going to be tested to 240. If there is a leak at 240 PSI, we're going to find it. If it's something that can be repaired, such as maybe a plug, they'll repair that. However, if it is at a tube roll, basically at that point, scrap the heat exchanger and you would start over. The reason being is if you've already pressed the copper out, if you over-rolled the tube, you've cracked the tube at that point, there's really not a way to replace it. If you've under-rolled the tube, then the problem is you go back and try to re-roll it, then the odds are very likely you're going to over-roll it at that point and crack the tube. In either case, it's a bad heat exchanger. So if there is a leak at a tube roll, pretty much just scrap the heat exchanger and start over. Once the heat exchanger passes the ASME test, then at that point they will affix the rating plate onto the heat exchanger with the pertinent ASME information, the national board number, the serial number, and the stamp. And then it can actually be used in a product. It can either be sold as a replacement heat exchanger or actually be used in production. So we have a couple of things we can do with it at that point. Now, as far as the volumes of these heat exchangers, like all copper heat exchangers, these are low mass. So that means they've got a very little water content in the heat exchanger itself. So as you can see, from 500,000, 3.5 gallons, up to 5 million, 15 gallons, not a lot of water in these things. To give you an example, the 2 million at 6 gallons of water. If you compare that to a 2 million BTU crest today, that heat exchanger has about 100 gallons of water in it, a little over 100 gallons of water in it. So again, a huge difference, same input, but a huge difference in water volume. So because of the low mass design, that means the flow is critical to the heat exchanger's operation and to its life. So that means piping comes into play. So with low mass heat exchangers, you must pipe these primary, secondary. There is no full flow option here. So it has to be a primary, secondary, and a hydronic heating application. If it's being used as a potable water heater, your smaller models can be sold as water heaters, then it has to be piped directly to a storage tank or tanks at that point. So again, we have very specific flow rates that we want to look at, and those are all listed in the installation manuals for the products. As I mentioned, the tubes, a lot of tubes here, right? For the 500 to 1.3, 20 tubes, 1.5 to 2 million, 24. And then when you get to the larger models, 62 tubes. There's a lot of tubes in those bigger models. So how do we get 62 tubes in this thing? Basically, we're adding dual coils, right? Each one of these copper tubes can only handle so many BTUs. So to be able to get up to 5 million BTUs, we have to have more surface area of the heat exchanger. So to do that, we add more tubes. So basically, we have 2 layers, an inner layer of tubes and then an outer layer of tubes. So how we get those all to fit together is going to be based on a brushing and swiping method. So this would be the tube that you would see in the larger models. So this is our standard copper tube. This is a 99.9% pure copper tube. We do have the option for Cooper nickel if someone wishes to do that, but the standard tube would be pure copper. Again, the fins as it comes in, it would be a thin copper tube all the way to the end. This is a good picture that shows the de-thinning process here. Shows where basically we've cut off about 1 inch of those copper fins from the front end here, as well as the back end to allow that to slide up into the header for the rolling process. Now, once we get the tube, we cut it, we de-thin it, it then goes over to another machine where they're actually going to swipe and brush these tubes over. As you see, you get this very specific pattern to it to allow the tubes to kind of interlock, if you will, or to kind of fit together. So we don't have so we try to minimize the footprint of the heat exchanger. So we're trying to fit these tubes better together. Also, doing that slows the flue gases down, gives you a little bit more restriction in the tube, slows the flue gases down, which allows a little bit more contact time on the tube, then gives you a little bit better heat transfer. All right. So again, as I mentioned, with 62 tubes, it takes a while to actually build this heat exchanger, to put this heat exchanger together. So it's kind of a time-consuming process. All right. Now, once we have that heat exchanger completed and it has the rating plate, and you can see the rating plate right here on the front of the heat exchanger. Now, for inspectors, we will put what's called a courtesy sticker on the back of the jacket. That will have the same information. They will duplicate the plate that's on the heat exchanger. Obviously, we don't want, if an inspector wants to see the plate, we don't want to have them opening up the unit to get to the heat exchanger. So there is a courtesy sticker. It's on the back, which is acceptable per code, that has the pertinent information against a duplicate. So they can look at that and they're going to be good to go. Now, once it goes to the line, we're going to add what's called V baffles. And as you can see on the heat exchanger pictured there, these are a series of baffles that fill up between the actual tubes. So there's going to be gaps between the tubes. And we want to put something in there that's going to force those flue gases to go through the path of the fins. If for some reason those baffles weren't there, and what's going to happen is your flue gases will then shoot through the gap, and we're not going to get as good of a heat transfer. Your stack temperatures would increase considerably. The heater would still fire and still operate, but your stack temperatures are going to go up because we're not getting the heat transfer that we should be getting. So the V-baffles serve a pretty good purpose, right? They serve a valuable purpose by filling those gaps up and forcing the flue gases through those paths. So we start with our base. They put our frame, if you will, the sheet metal, or in this case stainless steel box that forms our combustion chamber. Heat exchanger goes into that, and then we seal up the front door. So you see the completed box over here on the right side, if you will. Now, once we put the front door on, we're going to pressurize that cabinet to ensure that there are no leaks. So they're going to basically plug off the vent side. So they'll put a big plug, if you will, kind of in the back end here. They'll put a plate on the top of it, covering up the combustion chamber with an air spigot, and basically slightly pressurize that cabinet. And then check for leaks along the seams. This needs to be sealed airtight. If there is a leak in any of the seams from the combustion chamber side, well, you got to think about this. When you're running the heater's in actual operation and you're generating flue gases, I don't want those flue gases escaping through those gaps into the unit itself. If those flue gases then get into the heater, then that's going to start affecting your electronics, right? Your blowers, your boards, your wiring. It's going to start affecting these different components, which can lead to operational issues. So we want to make sure everything is sealed airtight at that point. Now, once it's passed that test, now we've got our sealed box. Now we can start adding everything else to it at this point. So now we start adding all the other components. Now I'm going to stop here for just a second to see if anybody's got any questions as I've been rambling along here. I'll take a drink of water. At this moment, no questions are in. Again, if you have questions, either type them in or raise your hand and I'll answer those for you. So we've got our box. Now we can start adding things to it. Now the first thing that we're going to add to the box is going to be our combustion system. Now, with our combustion system, negative regulation is pretty much the standard combustion system that we use on most of our products today. There are a few exceptions. One of those exceptions will be in the power fin line, and we'll talk about that in just a moment. But for the most part, negative regulation is what we're using across the board. Now, I'm not going to get into a deep dive on negative regulation here. If you wish to know more about that, we do have a video again online on Lochinvar U where we talk about negative regulation. We go into deep discussions about how this works. In a nutshell, when you get right down to it, it's all about airflow. All right, so as airflow goes through the venturi, we basically create a vacuum gas orifice. The stronger the vacuum on the gas orifice means we have a stronger vacuum on the valve itself, which causes the diaphragm in the valve to move. All right, so the more suction we put on the diaphragm, the higher the diaphragm lifts, the more gas flows out of the valve. So basically it's all airflow. So the more air you move through the venturi, the more gas you're going to pull through the valve. So as the fan ramps up, more gas flows. As the fan ramps down, less gas flows. Anything that affects our airflow affects our gas flow in a neg reg system. So that means vent length, air intake length, blockages in either one of those, right? Dirty filters, dirty burner, dirty heat exchanger. Any of these things that obstruct our air movement through the system is going to affect our airflow. Now in some cases, that can be a good thing. As if you have, say, a dirty burner and the burner starts getting dirty, it basically derates itself and protects the burner to a point. So sometimes that's a good thing. But again, it's all about airflow. You're not getting, if you're derating the heater, you're not getting max capacity out of it. You're not getting what you should be getting out of it. So we want to make sure everything is operating correctly and everything is doing what it's supposed to be doing. So airflow affects everything. So how does this start? So it starts with the blower. All right. Every unit's going to have a modulating fan on it. Depending upon the size of the heater will dictate the size of the fan. Now the fan itself will have two connections. Again, a power connection, which could be either 120, 208, 240, 480, depending upon the size of the product that we're dealing with. And then we have what's referred to as the PWM signal, or the pulse width modulation signal, which is what's actually controlling the fan. And that PWM signal is telling the fan when to start, when to stop, where to modulate to. It's controlling the operation of the fan itself. Now, the fan is being monitored by the control module. So the control module will send a signal out. It gets a signal back. And basically, that signal has to be, that return signal has to be within 30%. So basically, it's monitoring what the fan is actually doing. So if for some reason the fan is not operating as it should, the unit will sense that and then go into a lockout, and you will see either fan speed high or fan speed low lockout. And we'll talk more about that in a second. Now, something else that you'll notice, and you'll see it mentioned here, a fixed air orifice plate for the 502 to 2 million ones only. And the reason for the plate, all right, for your fans, for your models, from 500 to 1.3 million BTUs, all right, there is a fan. For, I believe, the 1.5 to 2 million, there is a fan. So you've got one fan that covers quite a bit of range, right? So say as an example for the 500 to the 1.3 million BT models, one fan. That fan has to be able to go up to 1.3, but then be able to go down to 500 plus whatever it can modulate down to, all right? So I've got a very large fan here. It can't go down that low. I can't turn it down low enough to allow it to work the way I need it to work. So in this case, we're going to use a restrictor plate, if you will, that goes on the discharge of the blower to basically control or restrict how much air goes into the burner for the smaller models. Same thing for the 1.5 to the 2 million. You got a single fan for those three models. Now, when we get to the larger units, the 2.5 to 5 million, right there, I'm going to have multiple fans. So I've got a fan for the 2.5 and the 3. I've got a fan for the 3.5 and the 4, and I've got a fan for the 5. So with those, you know, the 2.5 and 3 and the 3.5 and 4, they're close enough in input range. I can control the speed with the control module, sending the changing the PWM to be able to get it to where I need it to be. I don't need an air orifice plate on those models. Because of the greater ranges on the smaller ones, that's why we have that. So it's very important that that plate, if you're removing the burner and we take that blower off, you take that plate off, it's very important that that plate goes back on, because without the plate, as an example, let's say it's a 500 and you don't put that plate on, now you're going to be delivering the air for a 1.3 when it goes to max speed, which can grossly overfire the system, create all kinds. You'll lean it out more than likely. It'll probably flame out at that point. So you'll have all kinds of problems. So it's very important that that plate goes back in. So when you're disassembling it for your maintenance, your cleaning purposes, very important that it goes back together correctly. Now, as I mentioned, we're monitoring the feedback. So if the fan speed is out of range for whatever reason, we're going to go into a lockout. So when we get this call, fan speed lockout issues, you're primarily dealing with three possible issues, primarily. Either a fan, a control module, or the wiring. To be completely honest with you, in most cases, it's typically a wiring issue. We get back tons of blowers and control modules every year, and there's nothing wrong with them. Unfortunately, what happens in a lot of cases, people see the lockout, fan speed lockout, and the automatic assumption is it's a fan, and the fan gets replaced. And that doesn't fix the problem. Then they replace the next thing, which will be the control module. That's the next logical item, replace the control module. So you replace probably two of the most expensive components on the heater, and that's not been your issue. More often than not, it's typically a wiring issue, either due to a loose pin in the plug at the blower or at the control module, corrosion on the terminals, something of that nature. So before, and I always tell people this, before you replace a fan or a control module due to a fan speed issue, check the wiring first, check the pins, check the terminals first before you go any further. Now, if you do that, if you check the wiring out and the wiring checks out fine, there's no problems there, then yeah, it's going to be a fan or a module. We do have a fan tester that's available you can use to try to narrow that down. Basically, it will send a false signal to the blower, and it's looking for that feedback back from it. If it gets that signal that says, okay, fan's responding correctly, then the fan's probably not your issue. It's more than likely the module at that point. So again, it's one of those items more often than not. Now, with that said, if you've got anything that's pulsing power to the control module, such as some sort of safety switch, a flow switch, a block drain switch, an air switch, some other remote device like a tank thermostat, something of that nature, and we have ran into this before, if you have something that is pulsing power to the module, so if you're basically telling the module start, stop, start, stop, start, stop constantly, that's telling the fan to do the same thing. And that fan is going to try to ramp up, down, up, down, up, down. And eventually the module is going to say no more, and you're going to go into a lockout. So we have ran into this as an issue on various products. So if it's kind of a weird intermittent thing, check the externals. Is there something else tied in, or is there a safety possibly that's just bouncing power to it? So check your voltage, go through the wiring diagram, check your safeties, make sure there's nothing just pulsing power to the control module, okay? So we got our blower. So that's our main component. That's controlling the gas flowing from our gas train. So let's take a look at the gas train. So this is the next item. Now you'll notice here I've listed three control numbers, M9, B9, and F9, and we'll delve into this as we look at the gas train. So the first one there is M9. M9 is our standard gas train configuration, right? So it's a 5-to-1 turn down, fully modulating, all right? That's going to be our standard train from the smallest to the largest across the board. Now, B9, if we take it down to the next one, is for the 1.5 to 2 million only. All right. This is a minimal modulation, 2 to 1 at best. All right. In this configuration of B9, primarily we're using this where we're wanting to do a retrofit. Okay. This is a category 1 vented appliance. That means you're using B-vent, not category 4 stainless steel. So primarily you're going to use this in a retrofit where you've had a B-vent stack already established and you're going to go back with a B-vent unit. Now, because it's minimal modulation, my control looks at the flue temperature and it's going to control the modulation based on what the stack temperature is doing. So if the stack temperature is hot enough, it will allow the heater to modulate down. All right, and then as the flue temperature cools, once it gets to a certain point, then the control is going to say, okay, no more modulation, no matter how close we are to set point. We can't go any cooler because then we will then get into a condensing on the stack, in which would damage the B-vent, which we don't want to have happen. So the control module looks at that flue temperature on the B9 models and controls the modulation based on that. Now, F9 applies to the smaller models, again, 500 to 1.3. Same thing, retrofit applications. I've got an original power fin that was B-vented. I want to go back with a B-vent system. So again, category 1 venting. Here, we're going to go back to an F9 model, single stage on off. It's going to be just like it was before. But with this unit, we're going to change gas trains, and we'll look at that in a second. We'll see the different gas train here. So it's going to be a single stage on off, and it's no longer negative regulation. This will be a positive pressure system. All right, so it's a little bit different. Now, as far as our gas trains, the M9 in your B9 is going to consist of basically 2 components, a venturi and the gas valve itself, the modulating gas valve. I'll get it out in a second. Now the valve will change based on the size of the heater. All right, so anywhere from the what we call the blue top gas valve here, which is a Honeywell valve, up to the larger models where you get into the Dungs valves. So basically, you're going to have that modulating valve there, and then you're going to have a separate venturi, which is connected to the inlet or the suction side of the blower. And that's what's inducing that vacuum on the gas valve. Now, the valves themselves, 2 adjustments. Each valve will have a bias adjustment and a throttle adjustment. So there's always 2 adjustments on a neg-reg gas valve. Primary adjustments will be done at high fire, which will be done with your throttle. The throttle adjustment is basically just a window. It's all you're doing is just opening a window in the valve, which allows more gas to flow through the window. All right, so if I need to adjust to get my CO2 into range, I'm going to adjust the size of that window. So if my CO2 is high, I'm going to close the window off a little bit. If the CO2 is low, I'm going to open it up a little bit. So that's what I'm doing with the throttle. The bias adjustment, okay, is at low fire. And what the bias adjustment is doing is controlling the tension on the diaphragm. So remember, there's a diaphragm in the valve, and the suction from the blower, that vacuum that's created, lifts the diaphragm up. Well, the bias is controlling the tension on the diaphragm. So the more bias you put on it, the more tension you put on it, the more suction it takes to lift the diaphragm to get gas to flow. So we use this to control the low end, right? Or basically your idling speed, if you will. So at the bottom end, so we're controlling that side of it. So when we look at combustion, we look at high fire, we look at low fire, and we make adjustments as necessary. Now, this is assuming everything else is right. So before we touch gas valves, we want to make sure that everything else is proper. You know, the vent pipe is correct, the air intake pipe is correct, the filter is clean, the burner is clean, all of that stuff is clean. Again, because remember, airflow affects gas flow. So any blockages will affect our combustion. So before we start cranking on a gas valve, we want to make sure that there is a reason to do that. All right. Now, the valves that we're using here are dual valve seats. So that means that's why you just have a single gas valve. The blue one here actually has 2 indicator lights on it to let you know that the valve seats are actually energized. So a single valve, 2 valve seats. Now, when we go to the F9 gas train for the smaller models, and you won't run into these very often, but they are out there. Here you've actually got 2 gas valves. All right? And again, this is going to be a positive pressure combustion system. So if we actually measure the outlet pressure, in this case at the plug right here on this gas cock, On a neg-reg system, it would be a negative pressure is what you would see. It would be an actual negative number, slight negative number. All right. On the F9 model, you're going to read a positive pressure here. And for natural gas models, I believe that pressure is 3.2 inches, I believe, something like that. So don't hold me to it. You need to look in the manual, but it's a positive pressure. Now the valves themselves, okay, the first valve or the one closest to the manifold, this one right here, is your regulating gas valve. So that's the one you're going to adjust your pressure with. The other valve is just a standard open closed. Both valves will be energized together, so they're wired in parallel. So when you energize one, you energize them both. They both open together at this point. Then the regulating valve controls how much pressure goes to that orifice. So again, this will be an on-off type operation. You only see these in retrofits. I don't see a whole lot of them, but they are out there. So it's just something to be aware of. It is a little bit different than your standard M9 configuration that you would see. All right. So we'll stop here for just a moment. So I can stop a moment, see if we got any questions while I take another drink of water. So far, no questions, nothing on the Q&A. So obviously I'm doing a very great job. But again, if you got questions, please get those in, all right? So let's continue on. So let's talk about pressure switches. All right, here's the thing. With a negative regulation system, you really don't need a low air switch, all right? I don't need to prove that the fan is running on a neg-reg system. The reason is because if the fan doesn't operate, remember, no negative suction from the fan. If it's not operating, no gas flows from the valve. All right, so it's a fail-safe. So I don't have to prove that the fan is operating. Now, for the F9 model, however, that's why you see F9 switch there. For the F9 model, it's a positive pressure system. In this case, if you energize the valves, they're going to open and they're going to dump gas in, whether the fan's running or not. So I have to have some way to prove that the fan's operating. So we're going to use a low air switch. All right? A low air pressure switch is normally open set of contacts. So it takes a pressure increase on the fan side to make the switch. Now, one thing that you'll notice about both of these switches, for the F9 as well as for the M9, for the 500 through 2 million, is that they're differential switches. So basically, I'm looking at the discharge of the blower versus the pressure inside the combustion chamber, right? So because they're differential, it serves not only the low air function, but also serves as a block flue function. Right? So that means if something happens and the vent gets plugged up basically completely, and the pressure increases inside the combustion chamber, then that causes the differential between it and the outlet of the blower to drop. So if that differential drops between those 2 points, I don't have enough pressure there to make the switch stays open, nothing happens. All right, so it serves not only as a low air function, but also as a block flue function. Now, the F9 model has to have the low air switch, so it's there. It's per code, we got to have it. Now, the M9, however, the B9, really doesn't need a low air switch. It just needs a block flue switch. But at that point, because of the testing that we did and testing that we proved that, yeah, we got to have the block flue switch, we said, all right, we'll just use this differential switch because we already had it in stock. Right? So during the development of this product, this is what we had available. So we said, we'll just use this switch and make it consistent across the board. So that's why you see this low air switch, if you will, on the M9, B9, 500 through 2 million models. Even though I don't need the low air function, I just need the block flue function. It was just for expediency and consistency for us. That's all. Now, the larger models, the 2.5 to 5 million, when you look at it, it gets a different switch. So it gets a single pressure switch because, again, neg-reg, this is a normally closed set of contacts on this switch. So if the pressure inside the combustion chamber goes up, contacts will open, unit shuts off. All right. But you notice it says up there for 3 million to 5 million only. All right, why doesn't the 2.5 get one? All right. The reason the 2.5 doesn't get one is when we go through our certification, there is a test, and basically it's a block vent test. So what's going to happen is they're going to take the unit, they're going to fire the heater up at 100% at its maximum capacity. And then they're going to start blocking the vent off. As they're blocking the vent, they're looking at the combustion. So if the heater will shut off on flame signal or just shut off on its own before the combustion goes bad, all right, then at that point, I don't need a pressure switch. right? Because the heater is going to shut off on its own before it gets to the point to where the combustion is really out of whack, and I don't have to worry about it. My 2.5 million will do that. All right, it will shut off before we get to that point. The 3 to the 5s, however, would not. So that's the reason they get the switch. So I have to have the switch there to pass the test, if you will. So you'll see various products that will have pressure switches and some that won't. A good example, the FTXL models do not have a pressure switch on them because they all will shut down before the combustion gets to the point to where it's bad. So I don't need a pressure switch there. All right, but here we do. So again, 3 million to 5 million has to have the switch. So that's why you've got it. And again, in this case, it's a pressure only, positive pressure only. So it's a normally closed set of contacts, a block and vent switch. All right. So now we got our combustion system as far as the gas train, the blower, the pressure switches, and the safeties monitoring that. Now all that's then going to feed down into the burner. Right? So this makes up the last part of the combustion process would be the burner itself. Now your 500 through your 2 million. In this case, we're using a ceramic fiber mesh. So this gives it the orange look that you have see here. The inner liner is a stainless steel mesh screen covered by this ceramic fiber. The burner is kind of unique because it's kind of soft. So if you grab the burner, you can actually squeeze that mesh. Right? So you can bang it across the table and won't damage it. So you can do different things with it at that point. So you can kind of squeeze it. So you have that. Now the kicker with this is if there's, same with any burner, if there's physical damage to the burner, to the mesh, then at that point the burner would have to be replaced. So when we're taking the burner out for the maintenance aspect, for cleaning the burners, and the burners do have to be cleaned on a regular basis. So when you pull the burner out, you want to be careful as you pull the burner out that you don't drag it across any of the burner studs on the heat exchanger. Unfortunately, I have seen people do that where they drag that mesh screen across one of those studs sticking up there. It actually catches and gouges or rips the mesh material. If that happens, there is no replacement mesh. You just have to replace the burner. Because remember, what you're trying to do with the burner, and this is with any burner, you're trying to maintain a balanced gas-air mixture across the length of the burner all the way around in this case. So I'm trying to maintain a balance across the surface. If for some reason you put a great big rip in it at a certain point, well, the gas-air mixture is lazy, stupid, doesn't know which way to go, so it's going to go the path of least resistance, which would be through the gap. So now what you would have would be a huge flame coming out of that gap while everything else pulls into the burner surface. And then you're going to overfire the burner, you're going to damage the burner, you're going to burn the burner up. Under normal operating conditions, the flame never really touches the burner surface, right? The flame is always pushed off the burner surface. It stays away from it. This is where the run cool technology comes in at, that we talk about. If you've ever been to the factory, you've done the factory tour, you've seen the burner demonstration in our lab. If you've not had that chance, hopefully someday soon we'll be able to start inviting people back to the factory, and you can come, you can see this burner demonstration for yourself. But basically the burner is going to be running full tilt. Our lab supervisor, who generally does the demonstration, Jeff Cooper, will shut the burner off as it's running at its maximum and then immediately put his hand on it. And run his hand up the surface of the burner, which is very impressive because right before that, you just had this huge ball of flame sitting there, and he shuts it off and he puts his hand on it and doesn't come away burnt. So again, what we're doing is keeping that air forcing through the burner, which keeps the surface of the burner relatively cool. So that flame never comes in contact with it. When you get burner damage, and this applies to any burner, when you get burner damage, it's because the flame is pulling into the surface of the burner. And when you put that hot flame on the surface, that's when you get the damage. So that's what we're trying to prevent. So again, we want that balance from top to bottom all the way around. So we have ceramic fiber on the smaller models. Then we went to the larger models, the 2.5 to 5 million. We went back to the acro mesh material. This is pretty much the standard material that we use on all the other burners. The 500 to 2 million ceramic fiber burner is unique to that particular product. It's something that we wanted to try on it. Works well for there, but again, for the larger models, we went back to something that we already had a lot more experience with, and again, that was the acro mesh material. So in this case, we've got an inner stainless steel pipe that the material surrounds and setting on. It is attached only at a few points, so that mesh you can actually grip and twist, if you will. So now it's hard, so you can't squeeze it like you did on the smaller models, but you can actually move or twist that mesh around a little bit. Now again, same technology, the run cool, we're keeping that flame pushed off the burner surface. As far as cleaning the burners, both burners are going to be cleaned the exact same way. You're going to blow them out with air. As you see the burner sitting here, basically you want to kind of hold it upside down so the opening is at the bottom. You blow the air through the burner from the outside in, so that way you're reversing the pressure back through the mesh. A lot of times people will stick their hose down the inlet of the burner, if you will, trying to blow through it. Well, the problem with that is that's what your fan's already doing. So it's blowing stuff into the mesh. It's plugging it up. We want to reverse the process. So you want to go the other way. So we want to blow from the mesh side in and force the stuff back out of it. You want to take your time with this. So I see guys that'll just take their hose and do a once over it real quick. That's not cleaning it. You do need to go slow with the mesh, blow the mesh out in sections. Take your time with it as you're cleaning it. Even though it may look clean, on the inside, there's generally a lot of crap that you want to get out of it. So typically, blowing it with air, taking your time. Now, if you want to use water, some people always ask about using water to clean the burners. Here's the thing, with either the ceramic fiber or the acro mesh, if you use water to flush it out, blow it out with air afterwards, especially the ceramic fiber. The fibers can have a tendency, if it stays wet for long periods of time, can start to break down. But also with the acro mesh, it will rust if water sits on it for a long enough period of time. And it would take a while for that to occur, but it can rust. So if you use water if you have the burner out and you're blowing it, flushing it out with water, great. Blow it out with air afterwards, dry it off before you put it back in the unit, okay? So just do it that way if you're going to use it. But again, the way that we showed in the videos is just using air. That would be the way that would be recommended. So just take your time with it. Again, as you have it out, just again, make sure there's no physical damage to the burner, no rips, no tears, anything of that nature. If there is physical damage, then it's got to be replaced at that point. Now with the bigger models also, you will see on two of the models, the 3.5 and the 4 million, they're also going to get this diverter plate that you see here. Diverter plate, stabilizer, whatever you wish to call it, basically that is needed on those particular models based on the length of the burner itself, the size of the combustion chamber. During our testing, you would get a little noise from it. So to remove the noise from the combustion process, we put this device in here, which basically smooths out, or basically, I guess that's the best way to describe it. It smooths out or balances the gas air mixture as it goes into the burner. Your smaller models, the 2.5 and the 3, and your largest one, the 5, don't get it because based again on the length of the burners, the size of the combustion chamber, we didn't have those combustion issues. We didn't see those problems. It only arose with the 3.5 and the 4, again, just because of the things that went into it at that point. Again, the length, the size, things of that nature. So the diverter there helps balance that gas air mixture out in the burner and prevents the noise from occurring. So when you take the burner out, that's kind of pressed in there. I don't believe you can remove that. I don't think that comes out, but for some reason, if it did pop out at that point, make sure it goes back in before you put the fan back on top of it. All right. Now, how do we ignite this gas air mixture? All right. So our smaller models from 500,000 to 2 million, we're going to stick with our standard HSI, our hot surface igniter. All right. Any product from 400,000 BTUs and larger has to use a proven pilot ignition system. So this can be a proven hot surface igniter. It could be a direct spark ignition system with the flame rod. It could be a standing pilot with a thermocouple. There's different things that you could choose there. For the 500 through the 2 million, because of when it was developed, we went with the HSI. This is what we had available, and this is what we stuck with. So in this case, the control module, when we get to this point, when we need to power the igniter, it sends 120 volts to the igniter. The igniter starts to heat up. As it starts to heat up, it changes the amp draw. The amp draw characteristic changes. Now, there is a threshold that the module is looking for before it will start a timer. In this case, that threshold is 2.75 amps. So when it sees that, it says, all right, I've drawn the amperage I'm looking for. I'm going to start a timer. It's basically a 20-second timer. That's to ensure that that igniter As long as it stays above 2.75 amps, we'll get hot enough within that time to light off your gas air mixture. Now, for some reason, that amperage, say if it goes up to 2.75 amps, the timer starts, but then it drops below that. Well, then at that point, the timer will stop. All right. And then it's going to say, hey, we're not drawing the proper amperage. We're going to go into a lockout. It's going to say lockout HSI low, typically is what you would see there. All right. So we want to make sure that the igniter is drawing the proper amperage. Now, you can have an igniter that's glowing cherry or red, but still doesn't draw the right amperage. So we want to make sure that the igniter is doing what it's supposed to be doing. So if we're seeing this HSI lockout condition, we look at the amp draw on the igniter. It's got to be above 2.75 amps throughout its cycle. If it drops below that, it's a weak igniter. It's got to be replaced. Typical amp draw on igniters is going to be between 3 and 3.5 is generally where you see them run at. But again, 2.75 is our threshold. Now, once we energize the gas valve, then we've got a 5-second window to prove the burner flame in. Now, the control module will then switch and use the igniter as your flame sensor. So for 5 seconds, you have a 5-second window. The first 4 seconds will keep the igniter energized. And in that last second, it switches to look for a DC microamp signal. All right, the DC microamp signal I'm looking for is a minimum of 1 microamp. I have to have a minimum of 1 to actually prove the burner flame in. Generally, it's going to operate 8 to 12. Most often, it's where you'll see them run at. You might see it go higher. That's fine. It's not a big deal. The main concern that I have with the flame signal is that the flame signal is steady. Now, am I concerned if it's weak, if I see 5 microamps at high fire? That generally tells me it's a lean. It's a lean gas air mixture at that point. If I see a low signal at high fire, it's typically lean. Now, as the heater modulates down from high to low, yeah, that flame signal is going to drop, and I expect that. But at high fire, this is where I'm going to look at that flame signal, 8 to 12 is where I should be at. So if I see that signal a little bit lower, odds are I'm going to look at my combustion. I'm going to see my CO2 is probably going to be on the low end. So now I need to find out, why is my CO2 on the low end? Is there something derating the heater, or do I just need to tweak the gas valve? All right, so again, remember, before you tweak the gas valve, check everything else out first. But 5 to 15. I'm sorry, 1 microamp is what I need to prove it in. 8 to 12 is where we'll generally operate at. The reason you see 5 there is the control module, if it sees that flame signal drop below 5 microamps, the control module will then start forcing your modulation back up. So if you're sitting there and you're watching the heater run as normal operation, it starts modulating down. And if for some reason it starts to modulate down, then it starts to go back up a little bit, look at what your flame signal is doing. If the flame signal drops below 5, control module doesn't want it to go to 1, because if it hits 1, it's going to shut off. So if it says, hey, I'm at 5, I'm going below 5, that's a problem. So let's bump my firing rate back up here to make sure that flame signal doesn't get too low on me. So I got a question in from Jackson. He is asking, where do you check the microamps? Good question. Unfortunately, on this unit, you really can't check it. You're looking at the display. So the display is going to show you what that microamp signal is. Now, if you wanted to actually measure it, all right, there is a way of doing it. I've never done it myself in the field, but it does involve using a shunt capacitor, a meter, and a couple other devices. I've got a wiring diagram around here somewhere for it, but there is actually no test ports on the board to measure it. And you can't just put a microamp meter in line with one of these leads, because remember, you're running 120 volts through it to begin with. And if you do that, you'll smoke your meter. So what we're checking, where we're looking at the microamp signal, will be on the display itself on the current model. So the display will show you what that flame signal is. Okay. So hopefully that answered your question. But that was a good one. All right. So 5 to 15, again, as long as we're above 5, we're good at that point. Now the larger models, go here. Oh, sorry. Before we get to that, before we get to the larger models, I do want to show you this picture. The igniter is an OEM component, and this is what can happen if you use a non-OEM igniter. This is a copper fin 2, an older copper fin 2 product, and as you can see, it's kind of disassembled, and the reason is because of the igniter. This happened, and they had what we call a rapid expansion of gas and air inside the combustion chamber, and they basically sent the unit to us. This is how we received the heater. As we were expecting to find out what happened, we pulled the igniter out. The igniter we pulled out is the one that you see on the right side here. Right? What should have been in it is what's on the left side. So first off, you can see that there's a physical difference between the frame here. This one will not extend out over the igniter as far. But the biggest difference was the amp draw to temperature characteristic. Now, each one of these igniters has a characteristic. So again, what we're saying is on ours, we hit 2.75. That tells me we're getting hot enough. We start the timer to keep it hot, and then we open the gas valves. What happened on this one was we hit that amperage, but the igniter, even during that 20-second time frame, didn't get hot enough to light the gas air mixture. So it went to flame failure. Unfortunately for this gentleman, what he kept doing was he kept resetting it over immediately. After about the fourth or fifth time, the igniter finally caught. And when it did, we had this chamber full of gas and air, it lit off. And unfortunately, this was the end result. So when you're talking about hot surface igniters, you do want to be very careful and make sure that you're using the correct igniter. So yeah, there are a lot of igniters out there. Some of them will look a lot alike, but they all have different amp draw to temperature characteristics. So you got to keep that in mind. Make sure you grab the right one, okay? Now for the larger models, 2.5 to 5 million, here we're going to a spark system. So here we have a spark igniter as well as then a separate flame rod to prove the flame signal back. And again, we're going to look at that flame signal on the display. Same characteristics. I need at least 1 microamp to prove the flame in, but typically 8 to 12 is where we're going to be at. All right. Now, because I have an igniter and a flame rod, one of the things that you typically don't do with a HSI is clean them. You might blow some stuff off of it after there's maybe some buildup on it. You might kind of blow that off, but you never want to touch the igniter portion of it because you don't want to get the oils from your hand on the igniter or basically break the igniter. But when you're looking at a flame rod or the igniter and you get carbon buildup on them, you do want to clean them from time to time. Use a like a Brillo pad. Scotch Brite pillow pads, use that. Whatever you do, don't use sandpaper. I see that a lot. People use sandpaper to wipe that off. The problem with sandpaper is, again, sand is silica. And if you use that sandpaper on that rod, you can embed bits of that sandpaper, bits of that silica in the rod. And then when you heat it up, silica then becomes glass, which now becomes an insulator, which then insulates your rod, and you have a problem there. Realistically, the only times you ever need to replace rods or igniters is if there's either physical damage to the rod itself, like it's burned off to where it's no longer setting in the flame, okay, or if there's physical damage to the porcelain insulator causing something to ground out. Otherwise, you clean the rods off, put them back in, you're good to go. Now, sometimes people just do because of how they do it, their maintenance schedule. I have seen guys, they replace the igniters and the flame rods every year. That's just a yearly thing they change out. Before every heating season, they swap them out. If you want to do that, that's perfectly fine. I've got no qualms about that at all. If you do that, that's great. But it's not necessarily needed, right? I mean, the only time you need to replace them is if there's either physical damage to the rods themselves or to the insulators causing a grounding issue. So that would be something you would look at there, all right? Your spark transformer on these models, so will be this huge Allison transformer here. It's going to convert your 120 volt signal coming from the control module to a 6,000 volt spark going down to the igniter. So a lot of voltage there, very, very low current, right? So that means if you happen to grab a hold of the spark lead when it's sparking, it's not going to kill you. It might feel like it's going to kill you, but it probably won't. It's just going to hurt really, really bad. If you've never had the experience of being bit by a spark ignition system before, needless to say, if you're in the field, if you're in this business, that's something you need to have happen at least once so you can experience it and go, yes, I know what that feels like. If you come to the factory and if you've never had that experience, we can arrange that for you. Trust me, that can't happen. But again, you need to have that at least once in your life to know what that feels like, right? So you can describe it to people. No, I would not recommend that. That's not fun. Trust me. That's what's going to send the signal down to your igniter to light off your gas air mixture. So now we've got our combustion system set. Now we got to have something to control this whole combustion system. That's where we get into the electronics, right? So the heat exchanger was the heart. The electronics is the brain. This is what's controlling everything. So up front, we're going to have our LCD touchscreen display. That basically, that whole front panel here moves from the unit, hangs down from the front jacket, if you will. Right behind that will be our control panel. So here we're going to have our control module, our integrated control board. That comes a long way. All right. So you look at the original power fins, what you had in that control panel, right? You had a transformer, you had a pre-purge relay, a post-purge relay, a fan relay, a ignition module. You had separate thermostats. You had all these individual components that you had to keep up with. Here, you've got it all in one board. So you have a much thinner, if you will, much leaner control panel. So you just got one component that you're dealing with. Now there'll be depending on whether it's a boiler or a water heater, you may have a couple extra pump relays for a boiler, but again, not much. Nice thing about this, your control module is the same control module across the board. Whether we're talking from 500,000 to 5 million, it is the same board. How we can get by with that is that the program for every configuration is built into the control module. Now, how does the control module know which one to choose? That's based on what's called a personality plug. So up here in the upper left, you can kind of see the plug right here. Depending upon the wiring configuration in that plug, tells that control module, here's what program I want you to go find, right? So if I had a 5 million BTU boiler, right, that's what it's looking for. But I could take that board from that 5 million BTU boiler, put it in a 2 million BTU water heater, and it can work in that unit because it's going to look at that new plug. It's going to say, hey, do we really want to use this? If you accept it, it's going to find that parameter set for that particular control. And that's what it's going to go with. Now, I'm not going to get into the parameters of the control and all that because that will take way too much time. We do have webinars. We've already done webinars covering the smart system and the smart touch platforms. So again, if you've missed those, you can go back and catch those a little bit later. This is what you've got right here is your brains of the system. Will be your control module. Now on the back side of the heater will be our interface for your external items, right? This is our low voltage terminal board. So this is where we're tying in all the external stuff, all of our sensors, all of our remote safeties, things of that nature. Now, as the name suggests, it is low voltage, it's 24 volts. However, do me a favor, if you're working back here, if you're moving wires around, turn the power off to the heater. Okay, while 24 volts will just tingle when you grab it, it doesn't hurt. Okay? If you happen to drag voltage across some things, such as your cascade terminals over here on the right side, or your BAS terminals down here on the right bottom side, if you're dragging voltage across those terminals, you can take those functions out. The cascade and the BAS, those are digital inputs and outputs. We're talking ones and zeros. They do not like it when you drag voltage across them. So if you drag voltage on the wrong spots, then you release what we call the magic smoke, right? You release the magic smoke from the board, it no longer works. So we don't want to release the magic smoke. So turn the power off, move your wires around, do what you need to do to it. But this is where we're tying in all of our remote things. If you've got a question about where something needs to get wired in, if you look at this and go, I don't see what I need to wire into here. Don't just assume the pink wire is a good spot and hack into it, right? That's the one thing I hate more than anything else is when people start hacking into wiring, all right? That creates issues. If you've got a question about where something needs to get wired into, let us know. We will help you out, figure out where it needs to go to, okay? Just don't start hacking into the wires. All right, your high limits, right? You've got 3 high limits on this thing. There are 2 high limits that are built into the control module. They're part of the logic. So there's an auto and a manual reset high limit built into the control module. We'll talk more about that in a second. Then you've also got this auxiliary high limit, which is the gray dial high limit, which is also going to be on the front, will be sticking out the front of the jacket. All right. This one is there to meet code requirements, right? Now it's a manual reset, but it's going to be reset through the display. So you don't have the red push button here on it. It's going to be reset through the display. So 2 manuals, 1 auto. Now the limits that are built into the control module, we're using the outlet sensor. Right, so when we look at this outlet sensor, the outlet sensor is a multi-wire sensor. In this case, it's a 3-wire sensor. Right. Inside the sensor are 2 thermistors. All right, because I am using the board as my high limit, because I'm using the logic of the control module as a high limit, we have to use what's called a limit rated sensor. Right, what I mean by that is I have to make sure that the sensor is telling me correct information, right? So if I just had a single thermistor in this body and that single thermistor was telling me the temperature was 150 degrees. How does the board know it's actually 150 degrees? It doesn't. It says, all right, that one sensor tells me it's 150, but I really don't know it's 150 because what if the sensor's wrong? So in this case, we have to use a check system. So here you've got two thermistors, and the control module is going to compare both thermistors. All right, one's a 10K, one's a 100K. So basically, I'm going to look at them. They have to be within 10 degrees of one another. So I'm going to give you a little bit of tolerance there. They've got to be within 10 degrees of one another. If they're within 10 degrees, the control module is going to say, okay, sensor is reading correctly. It's reading properly. I'm going to display the one that shows me the hottest temperature. That's the one that you will display, and that's the one it's going to use. But we're good. All right. Now, if one of those was reading, let's say one was reading 180 and the other thermistor was reading 90, okay, the control module is going to go, which one of these is right? I don't know, right? Because one reads this, the other reads that. I don't know which one of these is correct. So if I don't know which one's correct, I can't trust what the sensor's telling me. So that means I can't use it. So then you're going to go into a lockout. It's going to say lockout outlet temp differential. That means you've got the temperature difference between the two sensors was too great. Generally, that just means it's a bad sensor. Now, it could be a wiring issue, so you do want to check the wiring, the plug, and make sure there's nothing disconnected there. But more often than not, it's typically a bad sensor, and you would just replace the sensor. So again, two thermistors within the body because it is a limit-rated sensor. So we have an outlet sensor. We've also got our inlet sensor. So the inlet sensor is monitoring the inlet temperature, outlet monitoring outlet. You've got to have them both because the control module also looks at temperature rise. It sees that the delta T becomes too excessive, all right, then it's going to shut the heater off because it says, hey, we've got a flow problem here. We can't have this. So if the delta T becomes too excessive, it's going to shut the unit down. So you got to have both sensors. You disconnect one sensor or one sensor fails, it's going to lock out on that particular sensor, right? Outlets, it's going to say inlet sensor shorted or grounded. Same thing for the outlet sensor, say the same thing. So again, make sure that the sensors are connected. There is a sensor shipped loose, which would be used as a system sensor or a tank sensor if it was a water heater. Do recommend using those sensors instead of just relying on the sensors inside the heat exchanger. If it's a water heater, you've got to use a tank sensor or a tank thermostat for the system to work correctly. I'd always recommend the sensor inside the storage tank. If it's a hydronic heating boiler, I would prefer to see what's going on in the system loop. So again, system sensor I would recommend using. All right. Then we've got a flue sensor. All right. Now, it's a category 4 appliance. I'm bitting it with stainless steel. I don't necessarily need to monitor the temperature in regards to protecting PVC vent, right? I'm not bitting it with PVC or CPVC or plastic, so I don't need to protect it from that aspect. So I've got a flue sensor here, but what's it really for? Well, primarily it's going to be used on the B9 model. Now, remember the B9, that for the 1.5 to 2 millions, min modulation, all right? So in this case, it's looking at that flue temperature. As long as the flue temperature stays hot, it'll allow the heater to modulate down. As that flue temperature drops below a certain point, it will then stop the modulation or force the modulation back up based on that temperature to protect the category 1 vent material. Now, for the M9 models, for your F9 models, basically it really serves no purpose. However, there is a limit to it. So I guess that would be your only purpose, to ensure that it doesn't get too hot. So in this case, if it sees that the stack temperature exceeds 400 degrees, that's going to limit the firing rate. If it continues to rise and hits 450 degrees, it will shut the heater off. Now, when it shuts off, it's not going to shut off on a lockout. It's going to go into what's called a blocking condition. It's going to say blocked high flue temperature. So what that means is if you still have a call for heat going, if that flue temperature drops 50 degrees and a 1-minute timer has expired, then it's going to say, okay, we can go ahead and fire back up. So again, it's not a lockout. It's just a blocking that says, hey, something's wrong here. We're going to hold up for a moment. Now, if you're seeing excessive flue temperatures, right, if you're seeing this issue, and you've got excessive flue temperatures, there's a reason for that. So what's causing that? Well, basically, we're not transferring the heat to the water. So that could be that our V baffles have fell away from the heat exchanger for some reason. Something's happened there with the V baffles. Could be that the heat exchanger is starting to scale up internally, so I'm not able to transfer the heat to the water properly. That means you just got to go up the stack. Okay? Or it could be that the heater is just grossly overfired. So somebody's played with the gas valve when they shouldn't have. We've given it a lot more gas than what it really needs, and we're just overfiring the burner. So there's a few different reasons that would cause that high stack temperature, but obviously it is an issue and we would need to address it. All right. And then we have an outdoor air sensor. This would be only on boilers and it is shipped loose. It's your choice whether you wish to use it or not. I always recommend it in hydronic applications. For heating applications, you want to be able to see the outside air temperature and change your water temperature based on that. The standard sensor is, as you see it there, it's a 2-wire sensor. It's going to get wired back to the low voltage terminal board. You do have the option for the what we would call the wireless outdoor air sensor. So basically you'd have a component that sits outside, then another component wired to the unit, but there are no wires between them. So that would be an option if you wanted to go that route. So you got a couple different choices there, but I always recommend using outdoor reset on hydronic systems because realistically you don't need 180 if it's 60 degrees outside in most cases. So you can lower that set point down. But remember, because it's a non-condensing heater, we got to be careful. If it's a non-condensing heater in a application where those water temperatures can drop below 130 degrees, so we want to put this caveat in here, because it's non-condensing, I don't want that inlet temperature dropping below 130 degrees. If it does, then we're going to condense on the heat exchanger, which would be bad. So in this case, if we're going to use a reset schedule, we do want to make sure we put some sort of low temp protection on the boiler, i.e. through a mixing valve, the low temp valve, whatever, and pipe it in that way. There's instructions in the manual for that. So I did want to throw that in there. If you use a sensor, outdoor air sensor, you're more than likely going to reset your schedule. The temperature is going to drop fairly low for your system, but we will still want to keep that temperature at the boiler above 130 degrees coming back so we don't condense on the heat exchanger. If you're condensing on the heat exchanger, that'll be real easy to see. You'll get this nice green patina on the heat exchanger, or if you get soot buildup on the heat exchanger, it's generally a good indication that you're condensing. All right. So that brings us to the end. That's a real quick run through of the various parts and pieces inside the power fin. So basically we're at the end of the presentation. I'm going to hang out for a few more minutes. So if you've got questions that you didn't want to ask during that, you can go ahead and ask them now. Again, you can raise your hand and I'll unmute you. Otherwise, like I said, the video will be up on Lochinvar U probably Monday. So you can go view it then or view any of the others. Otherwise, everyone have a great day. Have a great rest of your week and we will see you around. All right. Thank you.